Good morning, everyone. In this video, we are going to discuss about gas power cycles. Among the gas power cycles, we need to start with reciprocating engines. Reciprocating engines, they are classified into spark ignition engines and compression ignition engines. Spark ignition engines are petrol engines, and for the compression ignition engines, diesel engines. So the main parameter in the reciprocating engines, either spark ignition SI engine or compression ignition CI engine, and that is the compression ratio. What is the compression ratio? Compression ratio is the ratio between volume of maximum by volume at the minimum. So what is the maximum volume? What is the minimum volume in the reciprocating engine? So the piston position at the BDC, bottom dead center, is at the maximum volume, and the piston position at the top dead center, TDC, is at the minimum volume. So that ratio by volume at the BDC over the volume at the TDC, or maximum volume over the minimum volume, is considered as the compression ratio. And another parameter is mean effective pressure. So what is the mean effective pressure? That is the ratio between net work divided by volume difference. Volume difference, that is the displacement volume, which is equal to maximum volume minus minimum volume. So as given in the slide. And in the reciprocating engine, we do have two different engines, two different cycles mainly we use. One is the Otto cycle, either Otto or Otto you can pronounce. So Otto cycle, the ideal cycles for the spark ignition engines. If it is a petrol engine, we can say the word cycle, Otto cycle. If it is a diesel engine, we can use the diesel cycle. Okay, here actual and ideal cycles in the spark ignition engines and their PV diagram that we already discussed in the class clearly. So when we look at for the pressure volume diagram, which is having 1 to 2, 2 to 3, 3 to 4, and 4 to 1, 4 processes. So the first process 1 to 2 is isentropic compression. So the movement of the piston from position 1 to 2, from bottom to top, from BDC to TDC. And the second one for the ideal Otto cycle, 2 to 3, that is the constant volume heat addition. So constant volume process, the volume is constant, heat added to the system. And the next one, 3 to 4, isentropic expansions. So from the top position, the piston is moved until the bottom position. That is the isentropic expansion. And the final one is the constant volume heat rejection. That is the 4 to 1. So the PV diagram is very important for the ideal Otto cycle. So again, so the Otto cycle consisting of 1 to 2 isentropic process, 2 to 3 constant volume heat addition, and 3 to 4 isentropic expansion, and 4 to 1 constant volume heat rejection, 4 processes. And this is the TS diagram of an ideal Otto cycle. Normally, for 4-stroke cycle means one cycle is equal to 4 strokes, which is equal to 2 revolutions. For 2-stroke cycles, one cycle is equal to 2 strokes only, 1 revolution only. And this is the TS diagram. Here the S is the entropy. So constant entropy, 1 to 2 constant entropy or isentropic compression, 3 to 4 constant entropy or isentropic expansion in the TS diagram. And two-stroke engines are commonly used in the motor cycles and lawn mowers. And if you are taking the efficiency for the Otto cycle, or thermal efficiency of the Otto cycle is given by 1 minus 1 by R power K minus 1, where R is equal to maximum volume over the minimum volume. That is equal to V1 by V2. Compression ratio. In SI engine, the compression ratio is limited by auto ignition or engine locking. K is equal to thermal efficiency of the ideal Otto cycle as a function of K. K specific heat ratios, Cp by Cv. Either we can use K or gamma. That is equal to Cp by Cv. So these are the formulas for the Otto cycle, summary of the formula. So application of the Otto cycle, SI engines, example, petrol engine, LPG engine, CNG engines. For processes, compression ratio formula R equal to V1 by V2, that is the maximum volume by minimum volume. And the air standard efficiency or the thermal efficiency of the Otto cycle is 1 minus 1 by R power K minus 1, K or gamma we can use, and heat addition, constant volume heat addition at the process between 2 to 3, that is equal to Cv into T3 minus T2, and heat rejection is Q out Cv is into T4 minus T1, and the network equal to Q in minus Q out. So if we are able to find the network by heat in is equal to the efficiency. So either we can use the standard formula, a standard efficiency formula in terms of compression ratio, or we apply general engine thermal efficiency formula, that is work done by heat input. And next is the diesel cycle, the ideal diesel cycle for the compression ignition engine. Similar to the previous one SI engine, we do have 4 different processes: 1 to 2, 2 to 3, 3 to 4, and 4 to 1. I have given the PV and the TS diagram. Here 1 to 2 isentropic compression and 2 to 3 constant pressure heat addition. And for the 3 to 4, again isentropic expansion as similar to SI engine, and 4 to 1 is constant volume heat rejection. Here 2 isentropic and 1 constant pressure heat addition, 1 constant volume heat rejection. But in the Otto cycle, both constant volume heat addition and heat rejection. Here constant pressure heat addition. So small difference between Otto and diesel cycle. Okay, in gasoline engine or the SI engine, spark plug is, however, in the diesel engine, fuel injector. So in diesel engine, the spark plug is replaced by the fuel injector, and only air is compressed during the compression process. And again the formula, so including the compression ratio in the diesel engine, we do have another ratio, that is the cutoff ratio. So the cutoff ratio RC, or sometimes we use the density symbol, and that is equal to V3 by V2. So V3 by V2 is the cutoff ratio. So including both compression ratio and cutoff ratio, we have the simplified equation for the diesel engine. For the same compression ratio, the thermal efficiency of the Otto cycle is greater than diesel engine. And the summary of the formulas in the diesel engine, of course, application compression ignition engine, example diesel engine, truck engine, marine engine, and processes: isentropic compression, constant pressure heat addition, isentropic expansion, and constant volume heat rejection. So the additional thing is constant pressure heat addition, comparing with the Otto cycle. And the extra one, cutoff ratio. So the density formula or symbol or RC we can use, that is equal to V3 by V2. And then for efficiency formula have here, and heat addition is constant pressure heat addition. So Cp into T3 minus T2, and heat rejection is Cv into T4 minus T1, we can apply for calculating the heat rejection. So if you know heat addition and heat rejection, Q in minus Q out, we can find the work. And finally, thermal efficiency equal to work output by heat input. With that formula, we apply for finding the efficiency, or the simplified formula in terms of cutoff ratio and compression ratio that we can use. And the next one is the dual cycle. a more realistic ideal cycle model for modern high-speed compression ignition engines. So comparing with the Otto and diesel cycle, here we have 1 to 2 isentropic. This is the PV diagram, and 2 to X and X to 3. So 2 heat addition. So 2 to 3 or 2 to X and X to 3, 2 heat addition we have, and 3 to 4 isentropic expansion, as similar what we have isentropic compression in 1 to 2, and 4 to 1 heat rejection. So two places we do have constant volume and constant pressure heat addition. Both heat additions we do have in the dual cycles. So in more detail about the dual cycle and the formula related to the dual cycle, we will discuss in the next class. Thank you. And before, this is the summary of the equations for the dual cycles. So application of the dual cycle, modern diesel engines have the dual cycle. So heat addition occurs partially or partly constant volume, partly constant pressure. So the process is isentropic. First one isentropic compression, second one constant volume heat addition, and the next one is the constant pressure heat addition, two heat additions. Then again isentropic expansion and constant volume heat rejection. So the pressure ratio, in addition to the cutoff ratio, we do have a pressure ratio. So that is, we use alpha, P3 by P2, and air standard efficiency is a very long equation. When we have the comparison of the heat transfer equations, Otto cycle, diesel cycle, and the dual one. So the heat addition is 2. So constant volume heat addition and the constant pressure heat addition, two different heat additions. And heat rejection, as usual, constant volume heat rejections. So 1 to 2, 2 to 3, 3 to 4, 4 to 1. Have here addition, another one 5. 4 to 5 and 5 to 1 we can follow. Either we replacing with the X. That we will detail analysis we can do in the next week class. Thank you.